TMR. Here is the voting, and they are getting the same input. So, and here is the output. So if this is good and this is good and this is bad, your output, because it's based on majority vote, is going to be good. And of course, we have already seen that reliability of the system in this case is equal to what?
3R squared.
It works correctly, and let's see, is that the formula I want to use here? Okay, let me write it differently. So it will work correctly as long as all of the three modules are not bad, and you don't have the case when you have two of them bad. So it's actually the same expression as what you were saying, which is 3, what is that? 2r cubed minus 2r.
3R squared minus 2.
3r squared minus 2r cubed. So that's actually the same thing, if you simplify this way. And if you are, let us say that if your R happens to be 0.9, and if you plug that in, then that will imply our system equal to 0.972. And now, as I was saying, for highly reliable systems, it is often better to look at unreliability rather than reliability. So so basically, if you take R naught, that is 0.1, so probability that a single module is bad is 10%, and that implies probability that your system is bad equal to 0.2, 0.028. So probability that your system is not working correctly is about 3%. Okay. So you can see that there is a rather remarkable improvement, right? 10% probability that it is bad, and here it is only 3% probability that the system is bad. So you have a significant improvement, but this assumes that the failures are independent. And they did some experiments, and there are some famous papers, or they were famous at one time. There was a work by Knight and Levison. So they studied some software, and they found that there is significant correlation. So the failures are not statistically independent. So now, how do you take into account the statistical correlation? Actually, this is a problem that also arises with hardware reliability. So if you have a statistical correlation, then you have a significant probability of failure. Now, some of you may remember, or I guess maybe you may not. I would remember, but maybe for you it's... So there was this famous the space shuttle disaster, where the space shuttle, as it lifted off from Florida, it went up and then it disintegrated. That was a space shuttle. So so basically the space shuttle, so there's in the rocket, there's a ring of some rubber type material, which is supposed to seal it. And in order to provide redundancy, they have two seals. And so assumption was that one of the seal mechanism doesn't work, the other one would hold. But what happened is that the weather was cold there, so both of the seals shrank at the same time. So you had a correlated failure. Anyway, so that's on hardware. So a while ago I did a study of impact of correlation on reliability in redundant systems. And there are a few other people who have done some similar work. And unfortunately, you get into some mathematics. So problem is that if you assume statistical independence, mathematically it becomes very nice. You examine it, and with statistical independence, you can assume the failures are independent. It becomes much easier. And if they are not statistically independent, the mathematics becomes a little cumbersome. But I think that is another thing that something that people should. I'm hoping that some people will work on. So that is one of the one of the ideas I list in the suggested possible ideas, and so far no one has taken it up for the past few years. So, but you never know. Maybe there might be somebody who might think, okay, that's something I want to study. It's mathematical, but we are going to do something that is going to avoid the mathematics. We are going to look at some analysis that was done by Hatton. He's a British researcher. Now Hatton is not very strong in mathematics. If you look at his papers, he has some mathematics, not much. But he can come up with he usually has a good perspective. So he can see the picture, basically. So he came up with a rather simple analysis of the situation. So what he did was that he came up with a simple mathematical analysis so that he can use the data that was generated by the experiments that Knight and Leveson did, and use that data. He came up with an argument that even though there is significant correlation, inversion programming is a technique that is still worth considering in some situations. And this is an analysis. So let's assume here's the analysis. Let's call this an example. Basically, it comes from a paper by Hatton. So we have a 3-version system. And he considered Q3 is the probability, all 3 versions failing for the same input. Q2 is the probability that any 2 versions will fail together. And then he has a probability of system failing. Let's go to this middle of the board. So probability of system failing, and let me call it PSYS. So this is not the reliability, but the probability of the system failing for a particular input. And that is given by Q3, probability that all 3 versions fail plus probability that any two version will fail, and says it can happen with three different combinations. The probability that the system will fail is given by Q3 plus 3 times Q2. And these are the values that he plugged in, the values that were collected by Knight and Leveson. And so we are going to do that, but let's do it two different ways. First, assuming no correlation. And if there's no correlation, then he considered the number any single version failing. And according to a Knight and Leveson experiment for a transaction, is 0.0004. So, probability of the system failing, if there is no correlation, would be, in this case Q3 is going to be 0.0004 cubed, because there is no correlation. And this is, of course, since we are assuming there is no correlation, probability that two of them fail and one of them does not fail, right? So the probability of the system failing is 4.8 multiplied by 10 raised to minus 7 by a single transaction. And now let us consider the case when there is correlation. And for correlation, he took the numbers again from Knight and Leveson experiment. There is correlation. And so basically real numbers. From Knight and Leveson experiment. According to their experiment, the value of Q3 was 2.5 multiplied by 10 raised to minus 7, and I have rounded the numbers slightly, plus 3 times 2.5 multiplied by 10 raised to minus 6, and that is equal to 7.75 multiplied by 10 raised to minus 6. Okay, so how do they compare? This is a real number when there is correlation, and so you can see that the reliability of the system failure is higher by an order of magnitude, right? 10 raised to minus 7, 10 raised to minus 6. Actually, it's higher by a factor of about what? That's about 5, and this is 1 point. So it's like 15, 17 times higher. So the improvement, okay. So notice that the improvement factor